Okay, welcome back. Today is the last lecture on monodromy in this course on numerical algebraic geometry. There's several little topics related to monodromy groups of branch covers in the context of polynomial system solving that I'd like to touch on a little bit. Each I'll kind of say the necessary stuff. If you understand some of the background already, you'll digest this immediately. And otherwise you can just let it go. If you have questions, feel free to ask, of course, and we can delve into any particular one of these topics, depending on your interest. Okay. Okay, so this is our setup. We've seen this before. I'm gonna not messy up the parameter space right now with the discriminant, but you know it's there. So we have some parametrized polynomial system, say, and equations and variables, k parameters. And the parameter continuation theorem tells us this is generically a D1 map, where generically means restricted to the preimage of the complement of a variety downstairs. Okay. All right, and loops downstairs can be given a loop downstairs, you can follow the fiber over them using homotopy. Okay, so take a base point. This has some D solutions and a loop downstairs gives me some sort of, say, permutation upstairs. Okay. And so this is the monodromy map. It gobbles up loops, spits out permutations of the fiber. And today I want to go over just some ancient wisdom on monodromy groups. Specifically, I want to talk about how if somebody just hands you some branch cover, what should your expectations be about this monodromy group? Should you expect it to be really big? Should you expect it to be really small? Indeed, if you have a branched cover, that means the top space is irreducible. So you do expect it to be a transitive group at least on D things. But there's lots of choices for transitive groups on D things. So the wisdom is that monodromy groups are as large as they can be. This is not a mathematically rigorous statement. It's totally a heuristic. It's the kind of thing you tell your friends, but you don't write down explicitly. So unless there is a really good reason for a monodromy group to not be the full symmetric group, you should expect it to be the full symmetric group. Okay. So now I want to talk about at least one really good reason why something isn't going to be the full symmetric group. Here we have a function. And some functions can be written as the composition of other functions, and some functions can't. So it's totally possible that there exists B and psi and some other variety here, Z, say, such that pi is what you get when you first do P and then you do psi. So this is the situation I want to consider. What if somebody gave you a branched cover and they also factored your branched cover in this way? They did this for you. You don't have to find it or anything, okay? Then what do you know about monodromy? What do you know about this whole setup? So first of all, this is an irreducible variety. In fact, images of irreducible varieties are irreducible. Okay, that makes this an irreducible variety. All right, this is surjective. So this has to be surjective. So this is surjective. These are branch covers. Okay, so if you have a branch cover which factors in this way, it factors into branch covers. Okay, so if I have D points in my fiber here, how many points can I have in my fiber here? We know it's a branch cover, so it's finite to 1.
So divisor of D?
Yeah, it's gotta be a divisor of D, exactly, right? So, for example, if I take some point here and I look at the pre-image, I might have 4 points. Okay. But then if I wanted the fiber over pi, I would have to then take the fiber over phi of each of these. Right? And each of those is going to have the same size. Because phi is generically finite to 1. There's some generic number here.
So we chose phi to be specifically a covering map.
Nope. We just chose, somebody handed, we didn't choose anything. Somebody handed us phi and psi. Why does that look like a tower? Somebody handed us phi and psi as a decomposition of pi.
Mhm.
We concluded that these both must be covering branch covers. So that's a fact. If somebody decomposes pi in this way, you have 2 branch covers, which means both phi and psi are finite to 1 maps.
I can see why psi is surjective. Why is phi surjective?
Define, okay, so if phi is not surjective, define Z to be the image of phi.
Okay.
Okay. All right, so now what I've drawn on the board here is a 4-to-1 map and a 3-to-1 map. Coming from a 12-to-1. Now I want you to think about whether or not every permutation of these 12 points is possible by going around in loops downstairs. Rodwell shakes his head no.
Because
Give me an example. Let me give you a labeling here. Give me an example of a permutation which cannot occur in the monodromy group of pi.
the whole cycle, 1, 2, 3, 4, 5, 6, 7, 8.
Yes, can anybody think of a simpler one?
Transposition 1, 2.
Transposition of 1, 2 is going to be possible.
Transposition 1, 4.
1, 4 is going to give you a problem. Okay. So why can't 1, 4 happen? Why can't I swap these two? Because then I would have to be swapping their images, right? So as I go around this loop, I am going to get some permutation here, but I'm going to get some permutation here too. Let me call this A, B, C, and D. 1 and 4 are only going to swap places if A and B swap places. But if A and B swap places, then 2 and 3 have to become 5 and 6 as sets. So this partition of the 12 solutions needs to be respected in some way. Okay. So we're allowed to switch, a priori, we're allowed to swap A, B, C, and D. We have no obvious restrictions on what permutations can appear here. So this could be S4, for example. And then above each, there's no obvious restriction of how we might permute everything in one of these fibers. So it looks like pick anything from S4, and then pick anything 4 times from S3. Okay. So those are restrictions on which permutations can show. And now I want to jump over to permutation groups for a second on the other board and talk about what it means to be an imprimitive permutation group. So here we have the symmetries of the square acting on the vertices of the square. Okay, so this is a group of order 8. Sometimes it's called D8, sometimes it's called D4. It's one of your standard examples in your group tables. Okay. And I look at this partition of the things that are being acted upon. Let's give these names. B1 and B2. You'll notice that any action, so any permutation in D4, gives me a well-defined action on these two sets. Right? So for example, if I rotate by 90 degrees, 4, 1, 2, 3. Okay. Well then, 1 and 3 as a set have been moved to the other diagonal. Okay. And indeed, because this is symmetries of a square, I can't break apart the pairing of diagonals at all. So in other words, one so my permutation group doesn't just act on this set of 4 elements. It actually has a well-defined action on this set of 2 elements, where each element is a pair. Okay. We wanted to write this down mathematically. Any group element and any 2 elements in the same one of these sets. G is going to move it to a different set. G is going to move any element here to a different set, if and only if any other element gets moved to that same. So we're respecting this block structure. This is called a block structure. I'll say G now. And these are called blocks. Okay. So what do I think about when I think about block structures? You can think about this precisely with math, you can write it down. But how I want you to think about it is you have n people at a wedding, say. In this case, we have 4 people at a wedding, not very popular married couple. And they come in families. Okay, so 1 and 3 are a family, 2 and 4 are a family. My job is to seat them however I want. It doesn't matter who sits at what position in the table, as long as families stay together. So families can swap places. And then within them, the people can swap places. Okay, and the set of all such permutations of my 4 people at my wedding, induced this way, is a group. If I compose 2 of these swapping arounds, it's still a swapping around which respects families. And any group, which is a subgroup of that one, is called imprimitive. So.
Question for me.
Yes, give me 1 moment.
Sure.
Non-trivial here means there exists actual families. It's not like everybody is only in their own family.
Okay.
That's always respected, right? If everybody gets their own table, great, I'm just SN. Okay, and there's more than one family. Not everybody is sitting at one big table, because then I'm just SN again. Right? The subgroup of all terms with respect E will denote SB, and it is a wreath product, if you've seen wreath products before. If you haven't, that's fine. It's just the subgroup of all permutations which respects some log structure. Okay. So here D4 ends up being exactly SB. Okay. So let's think about how many permutations are in SB. Sorry. This means transitive. It needs transitive. I don't want to say anything about imprimitivity of non-transitive groups. Okay. Fact, if you're a transitive group and you respect the block structure, all the blocks have to have the same size. That's an exercise. Okay. Follows directly from this.
You wrote SB twice, like SB is equal to S size of B1 region. Oh,
Thank you. Okay, so what's going on here? We have 4 families. Every family has 3 people in it. Right? We have to respect these families. As we go around, whatever permutation happens has to keep everything in this fiber together. So I would say that this is S3, S4, or if I'd like, it's SB, where B is 1, 2, 3, 10. Okay. How many elements are in such a group? Almost. So if I have SA, read SB, or these are just numbers.
Three factorial.
I have B factorial choices for moving the families around. And then I have A factorial choices for moving all the people in each family around, but there are B families.
Ah,
So, for example, here, SB has order 2 factorial, because there's 2 families, times 2 factorial raised to the 2. That's 8.
because each will have that many amount of people moving on.
Yeah, I'm allowed to swap this any way I want. Independently, I can swap this any way I want. And if I want, I can swap people.
Yeah. Fine.
2 times 2 times 2, that's 8.
Hmm.
So SB is a group of size 8. D4 respects this, so D4 is a subgroup of SB, but also has size 8, so they're equal. Okay. If G is not imprimitive, we call it primitive. Again, only if it's transitive, otherwise we don't even talk about this adjective.
Are these all quotients of symmetry, like that one? Can we express it as a quotient group of Sn?
Yeah, look up Rithra.
Yeah.
And semi. Yeah. Okay, great. So fact. I is a branch cover. And pi is the composition of maps. Where phi neither phi nor psi is 1-to-1. Then the monodromy group of pi subset of S psi inverse all x so my blocks are given by the fibers. So this is maybe A in psi inverse of a U. And this is phi inverse. So those are my blocks. It's just what we said over here. Okay. So in particular, the prime is imprimitive. Any question? This condition here is the definition of a branch cover being decomposed. I is decomposed. And the statement is, if you have a decomposable branch cover, then the monodromy group is imprimitive.
Impacts. Okay.
What did I say just before cheese, so hard? Further down. Philosophy.
In particular,
Yeah.
but so this is what that statement says. Got a decomposable branch cover, you're imprimitive. This direction is true too. So somebody gives you some parameterized polynomial system. You solve it, you do a bunch of loops, and you find out that the monodromy group is imprimitive. Then you know there exists such a factorization. Now, can you compute it? That's another story, but you know it exists. We want to see an example of when this happens? There you go. So what's going on here? All of you know how to solve this by hand. Right, you do the change of coordinates, the monomial change of coordinates this. And then you do back substitution after you solve the quadratic. Sorry, you don't do back substitution, you just take cube roots. Okay. Okay, so what does that mean? Well, we have x is 6, plus 8x cubed, plus c. This is a 6-to-1 map. Because of the fundamental theorem of algebra. But it goes to. This is 2-to-1. This is 3-to-2. Okay. So you know your monodromy group is a subgroup of the Riesz product of S2 with S3. And all this diagram is doing is tracking what you would already do naturally. So this fact leads to a bunch of algorithm development of like how can I solve something of degree 6? Should I really be doing homotopy continuation from a degree 6 start system? Or should I reduce it, do homotopy continuation down here to find one of these fibers and then populate the fibers of these sequentially? Right, so that ends up being faster and more numerically stable in some ways, depending on how this decomposition is occurring. So one of the classes of parameterized polynomial systems we've discussed are sparse polynomial systems. Those are those polynomial systems where you've simply specified the monomials that have to appear in each polynomial, and all the coefficients are parameters. The story of when the monodromy groups are primitive or not is completely solved. So this was done by Esra. You have some sparse polynomial system. Okay, which is given by supports. You solved one in your last homework to verify your mixed volume computation. So if you have a collection of supports indexing such a sparse family, then either the monodromy group is SD, where D is of course the mixed volume of Yates by the PKK bar, or it is imprimitive. And I won't go into it, but checking if it's imprimitive can be done completely on the level of polyhedral geometry and lattice geometry. And this is going to give you a clue as to what kind of things are going to give you imprimitive Galois groups. Because this is just the sparse polynomial system supported on these monomials. 1, x cubed, and x to the 6th. Okay, and you are free to ask me more about that later, but I don't want to take up any more class time. The point is, Esra classified when sparse polynomial systems have full symmetric monodromy groups. Okay, and that's really, really important. we'll see how this is used in a strong way when we talk about trace tests. Okay. Any questions? Okay. Here's two circles. So X is a reducible variety. And I can project down to the x-axis. Okay. This doesn't look like it's essentially surjective over the real numbers, but it definitely is over the complex numbers. And in fact, if you ever pick a point downstairs, you're gonna have 1, 2, 3, 4 solutions upstairs. Again, it doesn't look like it over the reals, but this is a 4-to-1 map. It's not a branch cover. Because I asked for X to be irreducible when I talked about branch covers. But X does have irreducible components. And I can restrict this map to any one of them. And I do get branch covers. So if you find yourself in the situation where I don't know if the thing upstairs is irreducible or not, somebody just gave me a parameterized polynomial system, a lot of what we've discussed still works. You just do this trick. Okay, so I don't know if it decomposes. If it does have many components, then restricted to each component, I have a branch cover. Fine. Okay. I mean, I suppose it could be worse. I could also have this vertical line L. And restricting the projection down to the x-axis to L does not give me a branch cover. Because L just projects down to a point. So it's not essentially surjective. So this is the situation when the thing upstairs may or may not be irreducible. And you should know that a lot of the algorithms still work. Some of them don't. Monodromy solving won't work because you won't get a transitive monodromy group. There's nothing you can do to move these 2 points to those 2 points. Yeah, but that's the trick.
Is there anything to do with dimensions of those components?
Yeah, absolutely. So if you have a dominant map of varieties of the same dimension, then in particular you have a branch cover. Or if you have a finite map, varieties of the same dimension, you have branch cover. So this is restricted to L. This is neither finite because a point downstairs has an infinite fiber, nor is it dominant because the image of this projection restricted to L lives in a proper variety. Okay, but if you label a fiber, you could still theoretically write down some permutation group, right? We don't really want to call it a monodromy group, but you could. Okay. Yes, and so what this tells you is that if you try to do monodromy solving kind of like blindly, like you really just have one solution to your system over one point, and you try to populate all the solutions using monodromy, you're only going to get all the points in the fiber on the same component. Right, so if you try to do on a computer some sort of monodromy solving, and you find 6 solutions, you don't get to really conclude that generically there are 6 solutions. You get to conclude that generically there are 6 solutions as long as the variety upstairs is irreducible. Okay. So that's just a disclaimer and a warning. Okay, so that's decomposable branch covers and primitivity. You could call this a reducible branch. If you like. Reducible branch covers. I'm gonna wait on that. 2 statements about Galois theory. So Galois theory, i.e. like field theory, which you may or may not have taken, studies field extensions. and studies groups associated to field extensions. The monodromy group is a group associated to a field extension. Okay, so which, so U pi. And since you don't need to know this part for this course, we're not asking any questions about this on homework. We don't have an exam. However, this is the Galois group of the extension of function fields on your graph. Okay. If you have an irreducible variety, its coordinate ring is the quotient by a prime ideal. It's an integral domain that you can take that field of fractions like a field that's called a function field. The map pi gives me the inclusion of the function field of y into the function field of x. And so this is a field extension. It has a Galois group. It is the monodromy group. So this was proven out by Harris. Now, the thing I do want everybody to know, which uses this fact, but you don't need to understand any of this. There exists a formula in radicals in the parameters for a generic fiber pi if and only if G pi is solvable. Okay. You may not care about solvability. Solvability cares about you. Definitely if you're an applied mathematician, you care about this. There are lots of polynomial systems that people have to solve over and over and over and over again. They look exactly the same as each other, you're just wiggling parameters around. Okay, I think the example I use is when you're taking a panorama photo with your iPhone, it's gluing together over and over again, these snapshots it's taking, right? So it's a lot of the same kind of process happening, right? It's a lot faster to have formula than it is to do homotopy continuations. Okay, so people and applications are after formula, because then I can hard code that formula into your phone, right? And we can just evaluate this formula over and over again. I could even design specified hardware to evaluate this formula really fast.
Yes.
Because maybe I'm working in an application where cutting off a millisecond of something I'm doing a billion times is actually going to save me and give me an edge somewhere. Okay, I want formula. A Galois group or a monodromy group computation can prove the non-existence of such a formula. It could save you a lot of time if you're trying to find one. If you prove that the monodromy group is solvable, this is something you can just ask a computer algebra system. You don't even have to know what it means. If you prove that it's solvable, then yeah, start your journey on finding a formula, if that's something you want. Okay. What else do formula tell you? So you got the quadratic formula, and it tells you how many real solutions you have based on some inequalities, right? So formulas are good for real algebraic geometry too. And by the way, also for applications. So I appreciate that the applied people in the class may not pay attention or like or whatever this, but you should pay attention to this. Okay. Yeah, and those people who are more pure, if again you believe in these distinctions, you may be convinced that the things you're learning in your Galois theory course are very, very directly applicable to applications. Okay. That's all I want to say about that.
So, silly doubt again, but like, is unit step faster or Newton step? In the same predictor kind of thing.
The bottleneck for Euler steps and Newton steps is inversion of the Jacobian.
Oh.
They're equally small.
Oh, equally small.
I think so.
Okay. I mean, computing a formula that they might also use a Newton formula for computing the radical, right?
Right.
Like if you have something like a quadratic formula, computing the radical, you might use a Newton equation. Right?
Yeah, that's a good point. Even evaluating a
Yeah.
formula may include some similar things to the homotopy continuation.
Okay.
Yeah, I'm not sure, but no, no, I would probably just pre-compute roots of unity.
Okay.
Yeah, I'm not sure.
Hmm.
I'm not sure off the top of my head. Exactly, I hadn't thought that deeply into evaluating formulas fast on a computer.
Mhm.
Okay, great. When I gave you the monodromy assumptions, one of those was that the monodromy group is the full symmetric group. And I started this class today saying that that's kind of what you should expect. So as long as you don't have some other situation going on, which obviously restricts the monodromy group, you should expect full symmetric monodromy. In the sparse system, the obstruction to being the full symmetric group is exactly in primitivity of the Galois. Now that's not always the case. We're going to do an example in the computations where you do have a primitive group, which is not the full symmetric group as your monodromy group. But in any case, there are lots of situations where you want to know it's the full symmetric group. Okay. And there's a question of how do I go about doing that? Okay, so somebody gave me some parametrized polynomial system. Maybe I know it has 20 solutions because I just solved it in Julia. And I want to prove that the monodromy group is S20. So here's some facts. Okay, so here are two facts strictly from permutation group theory that can be translated into geometric things you might try to prove if you want to prove something has full symmetric group as its monodromy group. The first one involves a term we haven't used before, two transitivity. So if G acts on D objects, then G definitely acts on ordered pairs of distinct objects. I can think about it as living in SD choose 2. Sorry. Okay, I'm just gonna say this because my brain is blowing up right now. Ordered pairs of distinct objects. Okay, so think about like directed edges in a graph. If you act on the vertices, you act on the directed edges. Okay, if this is transitive as a group action, then this is too transitive. And similarly, you can induce an action on K-tuples of ordered elements. Transitivity of that action is called K-transitivity of the original action. So two transitive means not just if I take any two elements, I can move this one to that one. It's if I take any ordered pair and any other ordered pair, I can move this one to that one. Okay, so that's what two transitive means. But it corresponds to transitivity of some other action, which you can hook up a branch cover, which has that monodromy group. It's the fiber square. Do you know what this is? This will have monodromy group, which is this action induced. And So proving that your original group is SD involves proving this thing's irreducible. Okay, so that's a translation of two transitivity into a geometric interpretation. Containing a transposition can also be done. You choose something that's in the discriminant. And you show that you pretty much have distinct points up here, except you have one point coming with multiplicity in a particular way. So that means that little loops around this point on the discriminant can only possibly swap these two because all these are separated. Okay, and then you have to do a little bit more work to show that it actually swaps these two. All I'm saying is that there are group theoretic characterizations of the symmetric group, which can be translated into geometric problems that you can solve using geometry. This one, which isn't ever used, but I really like, says that SD is the only transitive group generated by transpositions. Here's my discriminant. I'm gonna slice it with a random line, which should have the same monodromy group above that line by the theorem from last class by Zariski. If over each of these, we have the situation where only 2 points come together. So over each of the points of this, so maybe a different 2 come together here, etc. Then the only candidates for these monodromy permutations locally around here, which you'll do on your homework, by the way, are simple transpositions. So if you know the only candidates are transpositions, and you know that you have a transitive monodromy group, you have to be the full symmetric group also. Those are 2 ways to prove this. Okay. And that is the first half of today's class. We will continue by computing the monodromy group of the problem of 27 lines on a cubic surface in Julia with not a ton of code. And we can ask questions to Gap through Oscar about this group. You know, tell us stuff. Okay. All right. So I will stop the recording. I will take questions. We'll take a 5 to 10 minute break.